Section 4.2. So far in all the examples that we've seen, the prediction equations have been provided, and we were just talking about the best fitting line would be called the regression equation on the previous page. And so now I'm going to give you a formula for how you can find that and show you how to use tables and that formula to come up with a regression equation. So the formula pieces come from calculus, so I'm not going to show the work here. But the format of your regression equation would be y hat equals b0 plus b1x. That's kind of our standard stat way of writing the equation of a line. And then the slope would be b1, and the way you get your b1 is to take the sum of the product of the deviations. So you take your x deviation, x minus x bar, multiply that with the y deviation, y minus y bar. You do that for every ordered pair, and then you add all those up. And then on your denominator, you do squared deviations of x, so you do x minus x bar squared, and you add all those up for all the different ordered pairs, and that'll give you your slope. And when you want the intercept, you take your average y, y bar, minus your slope that you just calculated over here, b1, times your average x, x bar. So let me go ahead and show you what the math looks like on that. Since we need x bar and y bar, it would make sense to start out by getting those first. So I would need to add up my x's, so it looks like those x's add up to 8. And so x bar would be the sum of the x's, which is 8, over the number of x's we have, which is 4. So x bar is 8 over 4, or 2. And then we do the same thing for y bar. We'd add up the y values. Looks like we have 1 plus another 10 would be 11 for the sum. And so y bar would be the sum of the y values, which is 11, divided by the number of y values, which is 4. And then you can divide that out, and in this case that would be 2.75. So there's your x bar and your y bar, and we're going to need that throughout both of these formulas. And then whenever you see a sum, you want to go ahead and make a column that has that heading, and then the total of that column would be your sigma, or sum of that. So when I see this sigma x minus x bar y minus y bar, I want a column that has a heading of x minus x bar y minus y bar, and then I want to do that for each of these 4 ordered pairs. So let me show you that kind of off to the side over here for this first one. I would do open parentheses, and the x is 1, minus x bar, which we have here, is 2, and then the y for that one is also a 1, minus the y bar, which is 2.75. And you could just put that into your calculator, or you could just work it out. In this case the numbers are fairly simple, but I'll go ahead and show you on the calculator what that would look like, because we could do this also with messy numbers. So I'd have 1 minus 2 in parentheses times 1 minus 2.75 in parentheses. And that gives us positive 1.75, so that would be this first entry right here. And just draw an arrow there so you can see where that one came from. And then we need to do that 3 more times for each of these other ones. And I'm just going to show you that on the calculator by editing the one that we had last, because our values of x bar and y bar are never going to change. As we go down the list, we could just hit second enter and say, okay, now my x is 1. Well, that's what it was before, so I'll leave that alone. And then the y value is 2, so I'll arrow in there and change the y value to 2, but the x bar and the y bar stay put. So that would be my next entry in the table. And then I'll do the next 2 as well. This time the x changes to 2, and the y is still 2, so we'll leave it that way. I'll do this on the calculator, but you can see the 2 minus 2, that's going to be a 0, so 0 times anything will give you a 0. And then finally on the last one, the x is a 4, and the y value is a 6, and we get a 6.5 for the product. So we had the 1.75 in our table already, and I'll just add these next 2 in there. We got 0.75 for row 2, a 0 for row 3, and 6.5 for row 4. And what we want there is the total. That'll be our numerator, so 1.75 plus 0.75 plus 6.5, so that's 9. So that's going to be the numerator on our slope. And then next we'd want to move through and do the squared deviations for all the x values. And I'll go ahead and write one of those down as well. So let's see, our first x value is a 1, and then minus x bar, which is 2, and then we would square that, so that's negative 1 squared, or positive 1. Go ahead and write that in there. And draw the connecting arrow so you can see where that one came from. and then we just want to do that a few more times. And I think we can actually do a lot of these in our head. This one's a lot easier. The x on the next row is still the same, so the deviation is the same. Here our x changes to 2, but if you put a 2 right there, 2 minus 2 would be 0 squared, which would be 0. And then finally you have the 4, and 4, let me just actually change that. 4 minus 2 would become 2 squared, or 4. And then our sum would be 1 plus 1 plus 4, which is 6. So now we can get our slope. Our slope is b1, and it's the sum of those deviation products, which was 9, divided by the sum of the squared x deviations, which was 6, and that is 1.5, or 1.5. That's our slope. We still need the intercept. For the intercept, you take y bar, which is 2.75, minus the slope, which was 1.5, times x bar, which was 2. And you could put that in the calculator just straight across, but I'm just going to do this one in my head. 2 times 1.5 is 3, and 2.75 minus 3 would be negative 0.25. So all the work is done. All that's left really is to write our answer, and our answer would be in the form that was given, y hat equals b0 plus b1x, where in this case b0 is negative 0.25 plus the slope, which is 1.5 times x. So that would be my regression equation. So according to those formulas and the calculus that produces them, this equation right here would produce the smallest sum of squared error for this data set. On the previous page we looked at a line A and a line B to see which one fit this data set better, and you might recognize this as line B. So not only did line B beat A, but line B is actually the best you can do for this data set. Alright, in the example above, I showed you how to find the linear regression equation by using tables and formulas, but that was a pretty time-consuming and messy process, and that was true even though our numbers were actually pretty nice. So of course it would be a lot easier if somehow we could just use the calculator to do the whole thing, and it turns out that we can. So I'm going to go ahead and show you how to do that. Just a quick note though, whether it's easy to do with a calculator or harder to do by using tables and formulas, linear regression should only be done if the scatter diagram or the scatter plot or the data plot forms a roughly linear pattern. So the rhetorical question there, why would you find the equation of a line unless your data has a linear pattern? There are other types of regression like parabolic regression, so if you saw a U-shape you might try and fit a parabola. Exponential regression, which would be better for curving data. So in this class we only do linear, but you still want to always look at a plot and make sure that a line really seems to be like the best fitting type of equation that you could do. So let me go ahead and show you how to do this last problem up here using the calculator. So I'm going to go ahead and start out by entering the data. So stat and then edit, and my lists are empty, so in L1 I'll put 1, 1, 2, and 4, and in L2 I'll put 1, 2, 2, and 6. So I've got my data in there. Then I'm going to essentially just let the calculator take over the rest. Let me go ahead and slide this up so you can see the buttons. I'm going to press the stat key and go over to calc because I want the calculator to do the work for me. And we do have two variables now, x and y, but we don't use that option because that would give us things like means and standard deviations. We want to do a linear regression, so this seems like a pretty good choice, but to have ax plus b, the slope term first, is kind of the algebra formatting. If you go down to number 8, you get a plus bx where the slope term comes second, and that's a little bit more of a stat way of writing things, so that would be the better choice for us. Actually, either one produces a correct equation, but 8 produces the equation that's correct and in the correct format. So I'll go ahead and press enter there, and it says, okay, I want to do a linear regression for you. And I just need to tell it where my data is. And I put the x values in L1, and then I'll hit the comma key, and then L2. So I want to tell the calculator that I want a linear regression where my x's are in L1 and the y values are in L2. And when I do that, it says, alright, the form of your equation is y equals a plus bx, where your a, or your intercept, is negative 0.25, and b, your slope, is 1.5. And if you look right here, we see that that's the same answers for the intercept and the slope that what we got when we did it by hand. So you can't just get the equation off of here, but you get the two key pieces, the intercept and the slope, and then it's just your job to write the equation down. You might be wondering what the r and r squared are, and maybe your calculator's not even showing these yet. We'll see these in later sections. For now, don't worry about it. When it gets time for us to use it, I will show you how to turn that on if your calculator's not showing that at the moment. Alright, so let's go ahead and take that skill we just learned on the calculator and apply that to our example for the Mustang convertibles. So the following are the age and price data for 12 randomly selected Ford Mustang GT convertibles between 1 and 7 years old. That's the same list that we saw in the earlier pages of the notes. And here X denotes the age in years and Y is the price in hundreds of dollars. And they've given us a sum of X, Y that will help us verify our data entry, so I'll show you how to use that as well. And their first question here is determine the regression equation of the data. You might notice that's part C, which seems a little bit strange, but remember we already actually have done a scatter plot for this data set on previous pages, and that's a good thing because we should never jump in and just do linear regression without looking at the scatter plot first. Like right up here, even if it's easy to do it, right? Why would we do a linear regression unless it was linear? But we did see that on previous pages that it is a linear plot. So let's go ahead and try and determine the regression equation. So let me bring the calculator in here and move the data over a little bit. So I'm going to just go ahead and repeat those steps. I'm going to go to Stat and Edit. I have data in there from our last example, so I'll use the up arrow to highlight the list name, clear and down arrow to erase, clear and down arrow to erase. And then I'm going to enter all those X values into the first list. And then I'm going to move over and enter the Y values into list 2. And then the calculator is ready to take over and do the linear regression equation for me. But if I have a typo on any one of these numbers, I'm going to get a wrong answer. So one way to verify that is to look at this sigma xy. If that matches, then most likely I've entered my data correctly. So let me show you how you do that. You go ahead and press the Stat key, and you go over to Calculations. And even though we want to do a linear regression, first we're going to check this sum. So we're going to do that by doing two variable statistics. And I'll tell it where my data is, L1, L2. And when I press Enter for that, I get a bunch of numbers like I had mentioned before, averages and standard deviations for x's and for y's, but if you scroll down far enough, it'll show you the sigma xy, 8492. That matches this. So when I see that I have a match there, that's a good indicator that I've entered all the data correctly, and so now I don't have to worry about typos. So now I'm going to go and now that I trust the data, I'm going to go ahead and do the linear regression. So I'll do Stat and Calc, and I'm going to go down to number 8, which is that linear regression in the format we use for statistics where the slope is second. And I'm going to tell it where my data values are, which are L1 and L2. And when I press Enter, it's going to give me the equation. So we don't have a rounding rule for this yet, so I'm going to do the safest thing, which is to go ahead and write all the decimals and digits on this, and we'll talk about the rounding rule a little bit later. So for right now, I'm going to say my regression equation is y hat. We always put y hat on our regression equation. And even though I'm going to put all of these, it still is a rounded off version, so I'll put approximately equal. And I'm going to do the intercept first, which is the A. So 293.2068966. And then I'm supposed to do plus bx, but in this case the b is negative, so that'll become minus 25.586. And then 2069, and that's the a and the b, but the equation is a plus bx, so I have to remember to do the times x here at the end, and people forget that a lot of times because they're kind of focused on writing all those messy numbers down, but you have to have a place to input your explanatory variable to output your response, or just a room for an input and an output, so you've got to have an x and a y hat in that equation. Alright, so that was a lot easier than if we had done that by the table. The table that we did up above, just go ahead and show you that again. That was a lot of work, and that was only 4 ordered pairs, and the ordered pairs were just single-digit whole numbers. So you can imagine if we were doing this one by table, and we did that with 12 rows and with messier y values, that would have been a pretty long and tedious process to go through, and maybe even hard to get through without a mistake. But when we use the calculator, we get a quick answer, and we can even verify that there was no mistake using two variable statistics and that sum of the xy's. Alright, let's see what's next here. Part D. What does the slope of the regression line represent in terms of Ford Mustang GT convertible prices? So the first thing is just figuring out like which one of these is the slope, and the slope is our coefficient of x, so that would be the negative 25.5862. I could write the whole thing, but I don't think I'll need that for the interpretation. This is probably even more than I need or want, but I'll go ahead and put that for now. And I always want to think of the slope as a fraction, so I'll put that over 1. And then I want to think of that as a change in y over change in x, only in this case our output's not y, it's y hat. So change in y hat over change in x. And then I want to put the units on. The denominator is change in x, and if we went back and looked at the problem, x is the age in years, so that would be 1 year. And the change in y hat, the y hat will always have the same units as the y, and the y value was the price in hundreds of dollars. So you might be tempted just to put a dollar sign on there, but it does say that it's hundreds of dollars. So when it says that, what you want to do is put your dollar sign, but with the number 100 there. And then you can multiply through by that. And when I multiply by the $100, I can move the dollar sign out front, and the times 100 will move my decimal over 2 spots. So this is going to move over 1, 2. And then I'm going to have $25.58.62 over 1 year. And then, as I mentioned before, I think it's usually best to interpret slope from the bottom up. So I would say for each additional year that goes by, the average cost of the Ford Mustang GT convertibles decreases by about $2,558.62. I'm going to go ahead and write that out. So for each additional year that goes by, and actually just rephrasing that a little bit, instead of saying for each additional year that goes by, I'm going to say for each additional year of age for the Mustang. And I'll talk about that after we write this out. And I'll say for the Mustangs. So for each additional year of age for the Mustangs, the average price decreases, and decreases because it was a negative, by about $2,558.62. Alright, so just a few comments on that interpretation. One of them would be things that people often forget. A lot of times people say for each year of age, and it's or for every year or something like that. It's important to say it's for each additional year of age, because the slope isn't telling you like how much a 6-year-old Mustang will cost. It'll tell you how much less a 6-year-old Mustang will cost than a new one. And then people often forget the word average. Y hat is our predicted value, and when we use predictions, we're always making when we use a prediction from a regression equation, we're always making a prediction of the average. So it's important we say it's the average price. Make sure we say decreases because it was a negative slope. And I think this is kind of important too. We don't know exactly what's going to happen here. This is based on just a sample, so this is an estimate. So I'd say it's about $2,558. And then just a quick comment on my change in wording. I started to say for each additional year that goes by, and then I changed it to for each additional year of age. This slope is not telling us like what will happen to a specific Mustang as time goes by. So the way I started to phrase that at first, it might sound like if you had a Mustang that was worth $25,600, then if you waited 4 years, then it would go down about maybe $10,000 based on that slope. But that's not what this says. It really says if you were looking at a 1-year-old Mustang and they were about $25,000 and you couldn't afford that, and you could afford something about $10 or $10,000 less, then you might want to look at a 5-year-old Mustang instead, because every additional year of age that a Mustang has on it, you expect the average price to be about this much lower. But again, it's not about one car going down in value, it's about if we switch from one age to another age, what that'll do to our average price estimate. Okay, continuing on with our Mustang example, they want us to graph the regression equation with the data points. So let me go ahead and bring our regression equation back in here from the previous page and slide that under so we can see both of them. So if I want to graph that regression equation, then I think one of the simple things that I could do to make that happen is make a little table of x inputs and y hat outputs, and then I could just plug in a couple values, plot those, and connect them with a straight line. So for my inputs, I usually like to use the far left and the far right of what I've set up on my grid. So we have this scatter, which we saw earlier on this problem, and I'm going to use the far left and right inputs of 0 and 8. The 0 I could do without a calculator. If I plug the 0 in, that's just going to wipe out this slope term, and I'm going to get y hat is approximately 293.2068966. Now I'm not that accurate by hand where I feel like I could plot that out to the 6th or 7th decimal place, so I'm just going to put 293.2, which honestly is more accurate than I can do as well by hand. And then for the second one, I'm going to bring in the calculator to help me with that estimate. So I'm going to type in the 293.2068966 minus 25.5862069, and then times, it's supposed to be the x right here, so that would be our 8. And when I put that in, I get about 88.5, so that'll be my other ordered pair. And with two ordered pairs, I could go ahead and draw the line. So I have over 0 up 293.2 and over 8 up 88.5. So over 0, this is 250, that's 300, so 293.2 would be pretty close to the 300, maybe right about here. And then over 8 up 88.5, if I just kind of try and mark this off across, that would be the 100 right here. So 88.5 would just be a little bit below that, maybe right about here. And then just a quick note that when I go to plot points that are from the prediction equation, I want to be able to tell the difference between those and the actual data values from my set. So these are the cars I collected data from. These X's represent just marks for me to do a better graph. So I'm going to line up with those two and draw in that line. And when I do that, really all I'm trying to do is make sure that that line seems like a decent fit. The calculus of the situation that gave us the formula says that when you use the linear regression process, you're supposed to get the absolute best fitting line that's possible. And so when we graph that, we should see that it's following the trend of the data. And so if we got a line that was over here or going upward or something like that, or not near the data at all, then we'd know that we had made a mistake. But when you see that your line is going through the data and following its trend, you can feel pretty confident that you've done a good job with that line. Alright, let's see what's next. Now they want us to start making some predictions. So use the regression equation that you obtained in Part C to predict the average price of a 2-year-old Mustang, a 3-year-old Mustang, a 40-year-old Mustang, and round your answers to the nearest dollar. So let me go ahead and show you what I would do there. I would just make a chart like we already have at first. And this time, instead of thinking about, well, I want 2 points that are far apart to make a good graph, I'm going to plug in whatever they told me to for the ages. And they want us to make predictions for a 2-year-old, a 3-year-old, and a 40-year-old Mustang. So I'll use all of those as inputs in this process. And then to get my outputs, I'm just going to go to the calculator and I'm going to just make changes from what I did a minute ago when I put the 8 in there. So I'll hit second and enter to get that last one back and change the 8 to a 2. And I'll do that one more time and change it to a 3. That'll be those first two predictions, and I'll come back and do the 40 in a minute. But first I want to go ahead and write those down. And just a quick note, they said to write these to the nearest dollar, and when people hear that, a lot of times they'll just round this to 242. But you have to remember that that digit right there is hundreds of dollars. So if that's hundreds of dollars, then this is tens of dollars, and that would be the ones place right there after we multiply by 100. So you'll see that a little bit better in a second, but I'm going to write each of these to 2 decimal places. So when I plug in a 2, I got out 242.03. And when I substituted in the 3, I got 216.45. But again, these y values, and actually they should be y hat values, are in hundreds of dollars. So I need to multiply by 100. That's going to put the dollar sign on, but it's also going to move the decimal over 2 spots and make this $24,203. I'll do the same thing on this one as well, and that will be $21,645. So they asked me to go to the nearest dollar, and you can see after I multiplied by 100, that was this 3 and this 5, which before I multiplied by 100 was 2 decimal places over. So if you're not sure on that, one thing you might want to do is just write a real long answer here, multiply by 100, and after you've multiplied by 100 and you know it's in dollars, then go ahead and round it off. All right, let's go ahead and look at that last prediction they wanted us to make, which was the 40-year-old Mustang, and see what happens with that one. So I hit second enter, change that 3 to a 40, and I press enter, and I'll put 2 decimal places just like all the others. So I get negative 730.24. We can multiply that by $100 just like we did the other two, and say negative 73,024. And I guess we could just move on and go on to the next part, but I think when you get a negative value there, you need to think about what that means. And this is how much it would cost to buy the average 2-year-old Mustang, and we're saying about $24,000. How much to buy the average 3-year-old Mustang, and we're saying about $21,000. How much to buy the average 40-year-old Mustang? Well, if you're going to believe our equation, it's saying negative 73,000. If I was going to interpret that negative 73, I would take that to mean that when you buy a 40-year-old Mustang, you have to well, it's negative, so instead of paying $73,000, they would give you $73,000. So you would get both the car and the money. And if that was true, I would be buying all the 40-year-old Mustangs I can. So this doesn't seem to make any sense, and I'm just going to make a note of this. Does not make sense. And you know, how much would a 40-year-old Mustang be? I guess that would depend a lot on its condition, but a lot of times that would be considered a classic car, so it might actually be pretty valuable, but it certainly wouldn't have a negative value. And when you get a prediction that bad, I think that there should be a warning that comes with that to kind of think about what went wrong. So let's go ahead and take a look at this warning box. Predictions made for X values that are outside of the given X value range are unreliable. It's unwise to make such predictions because the linear pattern may not continue beyond the data you have collected. Such predictions are called extrapolations. So when I went and made this prediction for a 40, this warning is saying that wasn't a smart idea because the data that I had only went from 1-year-old cars to 7-year-old cars. And so if I wanted to do the 2 and the 3, which is in that range, that's fine. But if I want to go outside of that range, that's where the warning kicks in, says that might not be such a good idea, you might get a bad answer. It doesn't guarantee you'd get a bad answer, it just says you might. It's more likely when you do an extrapolation on the outside than when you do an interpolation on the inside, like this 2 and the 3. The other comment sometimes people have is like, well, that's what I want to do, right? I have this data that's in the 1 to 7-year-old range. I want to use that to go on to 8, 9, 10, 11, maybe even 40. What's the point of doing a 2 and 3-year-old car if I already have 2 and 3-year-old cars? Well, you have one 2-year-old car, and when I look at it, it actually seems like a little bit of a high-priced car for the pattern. So when you use linear regression, what you're doing is trying to figure out the average price of 2-year-old cars, using the younger ones and the older ones to help figure out what that would likely be. And if you think about if you were trying to predict the price of a 2-year-old car, are you better off just knowing the price of one 2-year-old car, or also using what you know about 1-year-old cars and 3, 4, 5, 6, 7-year-old cars to help figure out what the average would be? In this case, it looks like if you just went off this one, you'd guess pretty high, but when you use the regression equation, you realize the average price is probably quite a bit lower. So there definitely is some value to doing interpolations, and there's definitely risk to doing extrapolations. So in statistics, we like to try and keep our predictions to be interpolations rather than those extrapolations on the outside. And the other thing that came up in here is when you do make a prediction, the y hat value always represents a prediction of the average y value for any given x value. So when I make this statement here that when I put in a 3 for the x, I'm going to get out $21,645, I'm definitely not trying to say that every 3-year-old Mustang GT convertible will cost this much, but I'm making an estimate or a prediction that that would be the average cost for all the 3-year-old Mustang GT convertibles that are out there. So our estimates are always predictions of the average, and that's why we want to make sure that we state that in our slope. And then as far as this last question goes, identify any outliers and potentially influential observations. Unfortunately, on this particular data set, I would say there are none. And I say unfortunately because it would be nice to show you an example of those. And I'm going to do that on the next page, but on this one I wouldn't, let's say there's not really any. If you were just to kind of have a quick sense of it here, but we'll see it better on the next page, an outlier or potentially influential observation would stand out quite a bit from the rest of the data set. If you asked me to identify one that stood out, I might think of this one, but it's to me not really a big standout value, so I probably wouldn't point it out. I'll mention this one, I guess. Maybe that's an outlier because it's a little bit, seems a little bit high for its age, but it's not an obvious one. So on the next page I'll show you a case of an obvious outlier and an obvious potentially influential observation. So on the previous page we were asked to identify any outliers and potentially influential observations, and I said that there weren't any. I also said that they would be data values that would kind of stand out very easily by eye. Let me go ahead and show you this picture down here and think about that same question. Are there any that really seem to stand out as different from the others? And I think there's two that are fairly obvious. This one seems to stand out, and this one seems to stand out. So let me go ahead and give you definitions of the outliers and potentially influential observations, and we'll try and decide which is which down there on that picture. So an outlier is a data value whose y value doesn't fit the pattern of the data set. And a potentially influential observation is a data whose x value is far away from the other x values in the data set. And it turns out that even though this one has the name potentially influential observations, both of these type of values can sometimes have a large influence on the equation of the regression line, and more so than some of the other data points. And so we always want to think about if there's a data value in my set that is having more say in how the regression equation turns out than other ones, I should think about what's going on with that value and maybe even ask questions like, should that be in my data set? Does it really belong there? So let's look at this picture and think about those two. When you look at this one, it has an x value that's in line with other x values. So let's just say that this was still cars and prices, and this was the age across, and this was the price in hundreds of dollars or thousands of dollars, whatever, on the vertical. Then what's going on with this one? It looks like it's a 5-year-old car that sold for way too little, or they're asking way too little for it. It just seems like if you look at the rest of the pattern, you'd expect that one to be much higher. So the x value is not strange. A 5-year-old car is not strange. We have 6, 7, 8 type-year-old cars, 4, 3, 2 over here. So the 5 fits in there, but the y value doesn't. You would expect a 5-year-old car to cost more, in this case like maybe around 70, 75 or something like that, instead of where it's coming in around 20. So I would say when I look back up at these definitions that that's a data value whose y value doesn't fit the pattern. And that is definitely off pattern, so I'm going to call that one an outlier. Whereas the other one I think does fit the pattern. If you think about the line that you might draw in for most of the data, this seems right on that pattern. It's just that there's this big gap right here, and that's an x value gap, because this is like a 20-year-old car, whereas this next closest one is 12, so we have this big age gap between those two. And when you have one where the x value is quite a bit over from the nearest x value, that's where you get a potentially influential observation. And I don't mind you abbreviating that at all, just make sure that you know what the actual words are, so potentially influential observation. So there's a better example of each of those two. And then just a quick discussion about why we would care. Well, as I mentioned a minute ago, these both have kind of a strong pull or say as to how the regression equation comes out. So we'd want to make sure that it was appropriate to have them in our data set. And one of the things we're always worried about with an outlier is that it might be an error. So when I see this one, I might go look at the data set again, and I wouldn't be surprised if I went back, looked at the data set that these all came from, and found out that this wasn't really a 5-year-old Mustang or car, whichever type. Maybe it was actually a 15-year-old one. And imagine that if it was a 15 and it was right here, that would be right on pattern. So then one of the questions that comes up is, since that would fit better over here as a 15, should I change it to a 15? And the answer there is no way, not just because it would fit better. I could only do that if I went back and looked at the original data and saw that this was a mistake, that it wasn't really a 5, it really was a 15. I can't decide it must be a mistake just because it would fit better here. And then what do I do with this if I go look up the value and it really is 5,25 or something like that, and that's not a mistake? And I said, well, most likely then I'm going to leave that one in there. We don't throw a value out just because it doesn't fit the pattern of the rest of the data set. The other thing I would mention there is, in addition to the numbers being wrong, it's always possible that it would be a different kind of car. Maybe this is in thousands right here, and maybe these are all Ferraris or something, and this one is a Mustang. So if it was another type of mistake that could happen is that I accidentally sampled something that wasn't from my real population. Interested in Ferraris, got a Mustang. So that would be a problem, and then I could throw it out too. But we don't throw it out just because it doesn't fit. The potentially influential observation is an easier discussion, I think. Should we keep it or should we throw it out? That depends on the kind of predictions we're going to make. If we're going to be predicting the price of younger cars in the like 2 to 10 to 11-year-old range, then I don't think we want a 20-year-old car having a lot of say in how that comes out, and I would toss that. But if I'm going to be making predictions of 14-year-old cars or 16-year-old cars, somewhere in this range, then I need that 20-year-old car to make this an interpolation rather than extrapolation. That data value is telling me the pattern continues, and that makes it valuable if I'm predicting the older cars. So if I was only dealing with younger ones, I'd probably throw out the one that was much older than all the rest of the data, but if I was going to do some predictions in this range, I would definitely keep that one. Alright, finally, I'm going to go ahead and give you the rounding note. When we rounded our equation for the Mustangs, I just put all the decimals in digits, and you could always do that. A lot of times I call that rounding rule 1, so I'll go ahead and even put that here. So rule 1 would be keep all decimals in digits. So that can be a little bit of a pain because the numbers are long, but if you write everything down, you're keeping the accuracy level high, and you can trust that the predictions you're making are going to come out accurate to whatever decimal place you're asked for. But it can be a pain to write all those, so then we have rounding note 2 down here, which tells you kind of the minimum that you could write and still trust your answers. So when you're writing an equation of the form y hat equals b0 plus b1x, you need at least one decimal place, you need at least one more decimal place in b0 than you want in your predictions, and you need at least one more digit in b1 than you want in your predictions. So what makes this rounding rule a little bit confusing is that when you're looking at the intercept, it's about decimal places, and when you look at the slope, it's about digits. So that can be a little bit tricky, and if you find that to be tricky, you can always just go back to rule number 1 and keep all the decimals in digits, which is a pretty safe move. But let me go ahead and show you how to use this rounding rule for the Mustangs. So round the equation for the Mustangs so that a typical prediction will be reliable to the nearest dollar. So let me start out by just copying down the prediction equation as we first got it off of the calculator a couple pages back. So we had y hat was approximately 293.2068966 minus 25.586 .2069x. So there's the rounding rule 1 kind of philosophy, which is, you know what, I'm just going to write them all and then I'm going to be fine. But if you want to use rounding rule 2, then what you want to do typically is go back to your chart and find the biggest y value you can. And in this case, the biggest y value was 289 for the Mustangs. And then think about, all right, but what was that price really? That was in the hundreds of dollars. So that was $28,900 was the cost of that particular Mustang. And I wrote that out to the nearest dollar, which would be right here. And then I want to think about where was that in the original number. When I had 289, where was that spot right there? And I would have to say that was 2 spots past the decimal place, right here. And then I want to think about that when I write out my equation. So I'm going to write y hat is approximately equal to, and this rule right here says that when I write my intercept, I need at least 1 more decimal place in my intercept than I had in this predicted value. So to get to the nearest dollar, I needed 2 decimal places, so I want more than that in my intercept, which would mean 3. So 293.207 would be the shortest answer I could write. Notice it is a 6, but followed by an 8, so I rounded it up. And I went 3 decimals in my intercept, so I could trust 2 in my prediction. When I switch over to do the slope, I change from decimal places to digits. So I look at this prediction and it had 1, 2, 3, 4, 5 digits in it to get out to the nearest dollar. So I need at least 1, 2, 3, 4, 5, 6 digits to be in my slope in order to trust a prediction that would have 5. So that would be 25.5862 and then times x. So this would be the shortest version of that equation I could give and still feel like I could trust the predictions that came out of it to the nearest dollar. And again, that's a little bit of a complicated process to go through, and for the number of problems you're doing, I don't know if it's worth it. So to play it safe, I would just probably keep all decimals and digits, but if you want to shorten it, then that's the process to think about it. Think about what your biggest y value would be, how many decimals would it have to get out to the nearest dollar, put at least 1 more decimal place than that in your intercept. How many digits would it be to get out to the nearest dollar, and put at least 1 more digit than that in your slope.